All right, so for the second part, this has to do with combinations, right? Which I think we have discussed with a lot of detail and in different ways. Another topic that's really interesting, but I think we won't have time to cover, and I should focus more on the things that are important for you and for the exam. I wanted to talk more about the inclusion-exclusion principle. We didn't cover that many examples because most of them are kind of cumbersome to write down. In case you're curious, let me tell you what the application is without actually going into detail. One application of inclusion, exclusion. And this will be another reason I want to maybe skip this for now. This will be most interesting to those students that either already took 246 in the past or have taken number theory or something similar. We can more or less easily find a formula for something that I think I may have written it down. We didn't talk about this. This was not part of the syllabus. But there's something called Euler's totient function. And it is important for many reasons in number theory. It will allow you to do many things that we didn't cover. For example, generalizing Fermat's little theorem defines something that kind of works like modular logarithms, right? That's not how you write totient. Totient function phi. Now, this function basically counts how many elements are invertible mod n, or how many elements are co-prime with n. Immediately, this doesn't seem that important unless you look at some examples and how this generalizes many theorems. But this will tell you, for example, how you can invert powers, which is what the logarithm would do, quote unquote. It's not exactly that, but something similar. And this plays a crucial role in cryptography as well. And this is something that you would use to encrypt and decrypt data using several different algorithms that use this idea that you can invert an operation that is basically exponentiation in modular arithmetic. So this is kind of long. If you want, we could cover this on Monday, unless if there are no questions or if people are interested in this. Maybe cover this on Monday. And if you took this course before 246, then you do know what this function is, but you didn't see a formula for it because it's actually not that easy to derive using just pure number theory. It is quite challenging, and many of the properties that are most important and simplify a lot of tasks with this function derive from the formula, which tells you how to calculate, how to compute it. And it's a shame that we didn't have time to do that last term. So we could do that this time because we know enough about combinatorics to give a simple proof of how to find that formula. But for now, let's focus on something else. The pigeonhole principle. And I've mentioned this in the past, but let's focus the rest of the lecture on giving more examples of the pigeonhole principle. How do you use? What does it mean? So here's one example that I like from graph theory, which says, I think it's called the handshake lemma. The handshake lemma might be something else. People, after a certain point, none of the names make sense anymore. The handshake lemma could mean something about counting the number of even degrees or something like that. Maybe I shouldn't even call it this way. Anyway, if you're seeing this video, then you could probably quickly Google this and verify if most people agree with me this is the handshake lemma or not. Should we just call it something else? Let's just call it, here is a neat observation. Here's a neat observation, okay? Let's say that you go to a party and maybe it's a really large party, like I think last weekend they had, there were music festivals, electronic music festivals, raves, that sort of thing, with a lot of people. And most of those people don't know each other, right? maybe if you go to like a small party that someone invited you to, or maybe you're even the host, then you might know a lot of people. But for larger parties, it might be the case that you don't know most people, or maybe you don't even know anyone if you're like crashing the party. But there's still some things that you can say if you want to impress your friends or your soon-to-be friends at whatever next party you go to. In any party, there's always two people that know the same number of people. Let me write that down. Any party. For some reason, many of these statements are phrased in terms of parties. Of course, you can make up whatever situation you want in any party uh, with at least two people. Otherwise, obviously, this isn't true. There are two people that know the same number of guests at the party. Of course, it has to be at the same party, right? If you know 10 million people and you go to a party of two people and the other person doesn't know anyone, well, this is not true. But of course, I mean at the party itself. Um, okay, maybe no is not the right word. That are friends. People, there are two people that are friends. The reason why knowing is not a good relation is because it's asymmetric, right? You can know someone that doesn't know you, that are friends with the same number of guests at the party. Any ideas why would this be true? What are the pigeons and what are the pigeonholes to make this statement true? And maybe I can tell you how I think about this. Pigeonhole principle is one of those things that's so evident, so easy, and yet many theorems that use this are quite difficult to wrap your mind around because it is telling you that something exists without telling you or giving you any hint as to how to find it. Something that you might try is you can try like dotting out a few examples. If there's two people at the party, if they don't know each other, well, they know the same number of people, which is zero. And if they know each other, well, then both know one. Okay, so with two people, it's easy enough. Add a third person. Maybe you want to do it like inductively. The problem is that it gets tricky, right? With three people, there are already three possible configurations. Wait, actually, that's not true. There are eight possible configurations, two to the three, right? They could all know each other. Maybe it's like this, but you see, things get a little tricky when you have a large party of, many, many people. Something like this. How do you make sense of this? Let's say that we try to make them all different, right? So the first one, let's say that they only know one person, and then the second one should know two, so that it's different from one, because otherwise we're done. The third person should know, maybe we can try so that they know three people, so that it's different from two. And then the fourth person should maybe know all of these, so that it's four. And then the fifth person should maybe know something like this. And oh, wait, then we cannot continue this. And these two already have the same number. These has one, two, three, four, and this has one, two, three, four, right? But this isn't really an argument because you may be able to sort them in a very different way. And if you try these configurations, of course, since this is a theorem, it is impossible to find a configuration where everyone knows a different number of people. But how do we prove this? How do we argue this using, logic and math? What is the proof? From now on, let's make sure all of our proofs are more or less informal so that we capture the intuition more than the formality, because here the difficult part is the intuition and not the formality. The formality is the technical part that we've worked so hard to polish over the term that now we can allow ourselves to focus on this other part. So any ideas? Why is this true? Why should this statement be true? Doesn't seem that obvious. also not difficult. So let me tell you how I would prove this. Sketch. So that no one says, but you proved this informally. So this is a sketch, right? So here's the idea. You go to this party and you want to figure out whether this is true or false. So maybe the party is at a large house that has a bunch of rooms in it, and the rooms just happen to be conveniently labeled for you in order of, an increasing order. The first room is labeled 0, the second room is labeled 1, 2, and so on, and they go all the way up to n minus 1. Let's suppose that n is the number of people, right? So n people, n guests. And you tell everyone, please get into whatever room corresponds to the number of people that you know at the party. Labeled like that. So each guest. Now, of course, they don't have to physically get there. This is a thought experiment, right? You can conclude this just by thinking about it. Each guest goes into the room whose number corresponds to the number of friends. So the person crashing the party who has no reason to be there goes into room number 0. The person who got invited by one friend but doesn't really know anyone yet goes into room number 1. The person that, whatever. The host maybe knows everyone because maybe it's a small party, so the host gets into room n minus 1. You cannot be friends with yourself, at least not for the purpose of this presentation or this proof. So the biggest number anyone could get to is n minus 1, right? There's no one in room n because that person would have to know themselves or be friends with themselves. Does this make sense? Are there any questions so far? Right now, it seems like this would still be possible, but where's the problem? There are n rooms and there are n people, so we cannot yet directly apply the pigeonhole principle. So what do we do? If the rooms are not the pigeonholes that I want, then maybe I need to get rid of some rooms, right? So here's the trick. The room n minus 1 contains all people that know everyone. If there is someone in that room, then there can be no one in room number 0 because the guest knows everyone. In particular, it would know everyone in room 0, right? So room 0 and the first and the last room cannot both have people in them because that would contradict the friendship relation, right? Whoever is friends with no one cannot be friends with those who are friends with everyone. And whoever is friends with everyone must be friends with those who are friends with no one, which is absurd. So this is the observation. So rooms 0 and n minus 1 cannot both be non-empty. Because if one of them is non-empty, it proves that the other one has to be empty. Maybe both of them are empty, we don't care, but both of them cannot be non-empty. Cannot both be non-empty. So only n minus 1 rooms can have people in them. Right? There are n people and n minus 1 rooms. So by the pigeonhole principle, one room has 2 people. And whichever room has 2 people, well, those 2 people know the same number of guests. And that's the end of the proof. why don't we take this to the next level? And this is something that is not usually taught in combinatorics since it's slightly, I don't know, I think I would call this an advanced topic, even though it doesn't seem that way from the easiest example of the subject. But here's a theorem that was discovered in the 1930s. That's 1930s by a guy named Ramsey. And this is just a generalization of the pigeonhole principle. Why will not be evident by the way I'm writing this, but you can rest assured that this is a generalization of this thing above. But of course, it's like a generalization on steroids. You can take this way, way farther than this, and this is a very it doesn't seem like a new field, but it is currently blooming again um, in different contexts. Okay, so what is the situation? It's the same situation in which you are at a party. At any party. This is not really what the theorem says. This is like a particular simpler case. If you're interested, you can look this up in your own time, or I'm happy to provide resources. The theorem itself is a bit more general, and it was not done in the context of combinatorics, but rather of mathematical logic. So this is like pre-processed and regurgitated in many different ways. Someone who does research in Ramsey theory would probably tell you that's not the theorem, but I'm not going to delete it this time like I did with the handshake lemma. This is fine. At any party with at least, that's at least 6 people, there are 3 that mutually know each other, or 3 that do not. Sorry, friends. Again, the knowing that are mutual friends. Now, this might seem obvious. Well, of course, either you're friends or you're not. What is the trick? But we want 3 that have the same relation between them, 3 at the same time, right? Now, let me tell you why this is false for 5 people. You need 6 people. 5 is not enough. Let's say that here are the people. Here's person 1, here's person 2, here is person 3, here is person 4, and here's person 5. Now, I'm telling you, I can come up with a configuration, with a possible party in which the statement is not true. For example, let's say that these people are sitting on a round table, at a round table, and they know the person to the left and to the right of themselves. So if we denote this relationship with a blue line, blue meaning friends, then everyone knows the person to the left and to the right, and they form a nice, a nice harmonic circle. The statement is false in this case. You cannot find 3 people with the same relation among them. Any 3 people will contain 2 friends and 1 not friend, or 2 non-friends and 1 friend. There's no way to find 3 people with the same mutual relation, right? If you color the non-friends in red, just to make things a bit clearer, you want, then you find this other nice cycle, right? Finding 3 people with the same relation is like finding a triangle of the same color. And the shape that I just drew for you has no triangles of the same color. There's no blue triangle, and there's no, why am I so bad at this? And sorry, let me focus on one thing at a time. There's no red triangle, and there is no blue triangle. Okay, that's better. Now, if I add one more person, then this is impossible. I must have a triangle. And you can play all you want with this, but how do we prove this? Can anyone think of a way to prove this? This was also in a math Olympiad in the 1940s, so this is not an easy problem. And if you take this to the next level, if you try to generalize this theorem, the idea is the same, but it is actually way more powerful than you might think. And I won't have time to connect these two ideas, but if you take this up a notch and generalize this just a little bit more, you can use Ramsey's theorem to prove the Bolzano-Weierstrass theorem that we mentioned in real analysis. So this is not something that is just contained in combinatorics and is a nice like party trick. This is actually connected to deep math that has implication in many other areas, including, like I said, big theorems mentioned in real analysis. I won't have time to tell you what the connection is, and it is not an evident connection. But maybe we can spend some time proving this because I think it's a neat little example of the pigeonhole principle. Okay, people in the chat are active. Okay, so why the triangle? So the statement is saying there's a party with 6 or more people. We want to find 3 that are mutual friends. What are 3 mutual friends? Well, 3 people. And all the relations between these people are blue because that's friendship, right? So it's basically a blue triangle. Now, I allow also to find 3 people that are mutually not friends. That is also allowed because, of course, maybe everyone is not friends. Maybe no one knows each other. In that case, I won't find a blue triangle, but I should be able to find a red one. Now, what I mean is that this party needs 6 people or more. Because with 5 people, I just gave you an example where there are no triangles of the same color. There's no blue triangle here, and there's no red triangle either. I say that this is impossible with 6 people. With 6 people, there will always be a triangle of the same color. Maybe everything's blue, maybe everything's red, but anything in between will still contain a triangle of some color. And the example for a 5 contains no triangle, right? You cannot find a triangle there anyway. Yes, you're welcome. Okay, induction. I like that idea, but induction would probably work more for the generalized case. In this case, there is no n to do induction on, right? There's just 6 and 3. There's something special about the numbers 6 and 3 that somehow puts these together. So let me tell you how I would solve this problem. So here's the proof of Ramsey's theorem. Again, sketch. It's the ideas that matter in this case. And before you ask, will Ramsey's theorem be on the final? Well, no, but applications like this will be, or might be, right? This is a very classical, simple application. This one's probably too hard for the final exam, but still worth paying attention to. Okay, so here's the idea. You go to the party, and let's say that you're person number 1, because labels don't matter, right? You're person number 1. And then you tell everyone that they should get into 2 groups. 2 groups. So all of your friends go to the left of the room, and all of your non-friends go to the right. So everyone here is connected to you with a blue line, and everyone here is connected to you with a red line. Maybe one of the groups is empty, then good for you, everyone's your friend. Maybe you don't know anyone, then everyone will be red. It doesn't matter, right? I'm not saying that these circles are non-empty or anything. So here are all your friends. Here are all your non-friends. And this is when things get really clever. So pay attention because this is actually quite interesting. This is the pigeonhole principle, maybe a slightly more general version of the pigeonhole principle, but it is the same idea. I claim that one of these 2 groups must have at least 3 people. And that is obvious, right? You know what? Why don't we write down the slightly more general version of the pigeonhole principle? We don't even need to prove this because it is so evident, but just because we only talked about pigeons and pigeonholes, maybe I should give you the slightly more general version. It's the same idea. I wouldn't even call this a generalization, right? So here's the idea. Now you have nk plus 1 pigeons, and you want to put them into n holes. Then 1 hole has not just 2, but k plus 1, right? So the example that we gave would be with k equals 1 pigeons. Why is this slightly more general, even though it's the same idea? Well, think about it this way. Suppose that the conclusion is false, meaning it is not true that one hole has k plus 1 pigeons. Then every hole has at most k pigeons, right? Fewer than k plus 1, so at most k pigeons. But if there are n holes, that means that in total you could have n times k pigeons. But that is a contradiction because I have more than n times k pigeons. I have nk plus 1. So it's the same idea, right? Barely worth writing down, but maybe useful. So in this case, one of these two groups must have 3 or more people, because if both groups had fewer than 3 people, meaning at most 2, well, there are 2 groups, each with 2 people or less. Well, that means that in total there's 4. But no, I have 5 people at the party, because with me there should be 6 or more, right? So one of these groups, one group contains 3 people or more, 3 or more people. Here's the brilliant part of this. You write people. Okay, let's suppose it's the friends, right? Let's suppose that we have 3 friends. If this isn't true, then just paint the non-friends blue. Like the colors don't matter, right? I made it up that it's blue friends and red non-friends. It could have been swapped. Clearly, the colors don't matter. This means that these 3 people are connected through me with blue lines because they are my friends. Now I ask my friends, do you know each other? Are you friends with each other? Do you happen to all maybe not be friends with each other yet? Then, you can introduce them or whatever. So there's 2 cases. Case 1, they are mutually, like none of them are friends with each other. In that case, these are not friends, these are not friends, these are not friends. And oh, there's a red triangle. Then, okay, so just to add a few more details in case you want to read this later. So without loss of generality, because all we are doing is colors, it's friends, right? There is a red triangle. Then there is. If they are all non-friends with each other, then I'm done. I found 3 people that are not friends with each other. But maybe that is not the case. Actually, between your friends, it is quite likely that they know each other, right? Because I think social dynamics generally tend to be in groups. So people tend to be friends in groups. I think it's rare that you have like a friend cycle or something. It tends to be like a friend network where most people are also friends. Um, there's actually an illusion related to that where this probabilistic argument. Anyway, let's not get distracted. So the case 2 is some of them, 2 of them are friends, right? The first case 1 is none of them are friends. Case 2 is, well, 2 of them are friends. And then you can see why we're done, right? Let's say that these 2 are friends, and then, oh, here's a triangle. 2 of them are friends with me. That's 3 mutual friends. And we're done, right? There's a blue triangle. So either there is a red triangle, or or at least one edge is blue, and then joined with all the other blue edges, well, I have a triangle, right? So either case, in all possible cases, there must be a triangle of the same color, and this proves the theorem. Now, if you really want to take this to the next level, this same idea works for graphs or for configurations that are much larger than this. But I think, yeah, I think that might be a little bit out of scope. Are there any questions about this? This finishes the proof, by the way. There is a triangle. There's plenty of things we can do with this. There are applications of this to number theory, to analysis, to set theory, to many other fields. This goes way beyond just combinatorics. But our time is limited. So let me give you a few minutes to ask questions about this. Like I said, this statement itself will probably, like, it won't be on the final. This statement itself, you don't need to memorize Ramsey's theorem. But arguments like this one, maybe not as sophisticated, is something that you should keep in mind. You know, just classic applications of pigeonholes. Okay, there are no questions. So either this was too easy or too hard. Does it make sense? Is the statement clear? The slightly more general pigeonhole principle. Okay. Okay, great. Great. People are saying yes in the chat. That's good. All right. Maybe we can do one more example of pigeonholes, and honestly, we could try to generalize this theorem, but it could get a bit tricky if we do that. Let's just do something simpler. Here's another example. Oh. Okay, let's do one easy example, and if you still have energy, we can do one hard example. Here's another example. We have a matrix. Let M be a 3 by 3 matrix of 0, 1, and -1. These matrices have a name. They're called like purely stochastic or something like that. I'm not really sure, but we don't care. So for example, the matrix could have something like 0, -1, 1, 0, 0, 1, -1, -1, 1, right? That's a valid 3 by 3 matrix that only has entries like this. So prove that the sums among the sums of the columns. So we add each column and we get a number. We add each row and we get a number. And we add the diagonals too. And we get all these possible combinations of sums. And I claim that two of them are equal, no matter how we put the matrix. Now, let's prove this. These sorts of short problems don't really require a formal proof, just the idea, right? Instead of writing a bijection and all sorts of things, it's the clever way you combine this or reduce it to something you've done in the past that's important. So any ideas? Why should this be true? If you take the columns, right? Take the columns. You take the rows. You take the rows and the two diagonals. This one. Two are equal. Two of those numbers are equal. Why can't they all be different? This is a good example, I think. So what do you think? Okay, so let's see. Okay, yeah, I already have the correct idea in the chat, the direct chat. There are only 7 outcomes. Indeed, there are 8 sums, right? 3 columns, 3 rows, plus 2 diagonals. That's a total of 8 sums. But each of these sums consists of 3 digits being added, 0, 1, and -1. But there are only 7 possible sums, which are -3, -2, 0, and so on, all the way to 3, right? You cannot get anything bigger than 3 or smaller than -3 because you only have 3 numbers. So there are 7 possible sums, but 8 of them, so 2 of them must be the same, right? Okay, this was simple. Let's see if we can find okay, why don't we do something way more sophisticated? Let me just think about whether this will make sense or not. This is pretty cool. So this is out of scope. So this is out of scope. This will not be mentioned in the final, but we don't really need anything to solve this other than things we've already done. I think we'll have time for this. So this is a theorem by someone named Schur. And the theorem says as follows. Color the integers, the positive integers, in 2 colors. This is just a way to say if we have the positive integers, we're splitting them into 2 groups, right? It's a partition. 1, 2, 3, 4, 5, 6, 7, 8. And let's say that this is red, 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 and the other ones are blue, 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 right, whatever. And you do this forever. Then the theorem says there is a solution to the equation a plus b equals c, all of the same color. Or let me write this in a better way. There are b. There are 2 numbers such that when you add them and you consider the first 2 are all the same color. And this is completely far from trivial, right? So you have 2 numbers and they need to be the same color. And when you add them up, you still want to get the same color. Can anyone find a solution that's already present on the screen? Maybe we can. So the original proof goes something like this. Pretend or assume that there are no solutions, and then you try to destroy all the solutions by finding a coloring and show that that is impossible. 2, 4. Okay, so 2 plus 4 is 6, and all of them are red. That's good. 3 plus 5 are blue, and 8 is the sum, which is also blue. So maybe I didn't make this hard enough. Okay, should we just, just for the sake of argument, try to make this a little bit harder? Okay, let's say 1 is red because the colors don't matter. 1 plus 1 is 2, so I should make 2 a different color. Now 1 plus 2 doesn't matter. 2 plus 2 is 4, and I don't want that to be a solution, so 4. Same reason 8 should be a different color. Those should alternate. Let's see. 1 plus 4 is 5, so that shouldn't be red, otherwise I have a solution. I think I'm about to prove this actually. 2 and 7, sorry, 2 and 5 is 7. Let's see, what else? How do I get 3? 4 and, oh, Okay, I think that's pretty much it, right? There's nothing else that's determined. So 3 and 6 are not determined. And then you would have to divide by cases or something like that. But here's a neat idea that tells you that you can always solve this. And this is, I think, really cool. Like I said, this is out of scope. Like these sorts of techniques won't come up in the exam. But there's nothing that we haven't done, right? So here's the trick. And this is quite magical, so I want to maybe draw this very, very large. So let's say that these are the numbers 4, 5, 6. And we could need more, right? There's no reason to believe that this cannot be more. So let's copy the colors from above. So this is 1, 4 and 7. Okay, 7 is not there anymore. That's okay. Let's say 2 and 5. And just for the sake of argument, okay, sorry. 3 cannot be blue because 2 plus 3 is 5. So 3 has to be red. And then 6 probably doesn't matter because I will have solutions anyway. 3 plus 3 is 6. Make it blue so that it's a bit more complicated. But there should already be solutions, right? 3 plus 4 is 7, which are all red. Okay, so what was I doing? Yeah, 6. So these are the numbers that I have. So here's the trick. I am going to color the relation between them. For example, 1 and 2 have distance 1, and 1 is a red number. Actually, these colors are not helpful at all. I think that will just confuse you. So 1 and 2 are consecutive numbers, and 1 is a red number, right? So I copy this down here, and I make all of these red. Okay, 1 and 6 are not consecutive, right? Because this thing could be way bigger. Now 2 is a blue number, so numbers with distance 2 should be blue. And I'm basically making friends, right? Friends and enemies at an imaginary party. 3 is red, so 1 and 4 should be enemies because they have distance 3, and 3 is red. 2 and 5 have distance 3. 6 and 3, 6 and 3 have distance 3. 5 is blue, so I only have to color in this one. And I think that's it. Everyone has, actually that's not it, right? Sorry. 4, why did I miss a few 4s? This 4. Okay, is it done now? Okay, I think I'm missing 1 for some reason. 1 and 5 is 4, right? Okay, now it's complete. Okay, so I basically made a party using these colors. Do you see? If the difference between two people at the party is blue, well, then I make them friends. And otherwise, I make them non-friends. Now, as you can see, Ramsey's theorem says that there must be a triangle here somewhere. And if you paid attention, you can actually spot one right here. So here's a triangle. This must exist because of Ramsey's theorem. Right? Is this good? Yeah. So by Ramsey, there is a triangle. There's a triangle, one triangle, like the red one we have here. Now, just look at this triangle and tell me what you see. 2 and 6 have distance 4. 2 and 5 have distance 3. 5 and 6 have distance 1. And indeed, 1 plus 3 is 4. And these are the distances, so they are all the same color. It's a bit like magic, no? And this works for any numbers. You don't have to start with 1, 2, 3, 4. You can shift this and start with other numbers. You can start this whatever you want. Now, there's something worth pointing out. Here, 1, 3, and 4 are all different numbers. Now, that's not necessarily the case. Like I said in one of the first colorings that I brought up, 2 and 2 and 4 were blue. 2 plus 2 is 4. So they could repeat themselves. So my question to you is, can you prove that you can not just find two numbers, when you add them up, you get all the same colors, but can you make A and B different? Like, can you change the theorem and say A and B should be different? And interestingly, the answer is you cannot do that with just 6, but you can do that if you make it bigger. And if you want if you want to have your mind blown even more, if I want to force A and B to be equal, then the theorem is false. In other words, there is a way to color this such that all solutions with equal numbers are destroyed. Even though this result wasn't too difficult to prove, this connects to many other weird ideas. So there are generalizations to this that go way beyond what I just did now. You could add more colors. You could have more complicated operations, not sum, but maybe multiplication, or maybe a combination of multiplication and addition, or something like that. More colors, more numbers, right? But I think it's best if I don't write more of this down, otherwise this will get too long. Okay, so there are like 12 minutes left. I will stay here should you have questions, but I will stop the recording for now. If you haven't already, please fill out the course evaluations. You can do so, I believe, on Acorn.